Good morning. I'd like to welcome everyone to Bandweaver's latest webinar, Going the Distance, Fire Safety Solutions for Long-Range Assets. So a bit of housekeeping first. The presentation will take approximately 45 minutes, after which we'll have a question and answer session, and you can submit your question at any time using the button at the bottom of your screen. And we'll do our best to get through them all at the end. If we don't get to your question, then we'll also be sharing Richard's contact details so you can reach out directly afterwards. We'll also be sending you the recording afterwards, so there's no need to take any notes or screenshots, and you will shortly have access to the whole webinar to rewatch in your own time. So just to introduce Richard, Richard has more than 20 years experience in applying monitoring and instrumentation technologies in a wide variety of industries, including upstream, downstream oil and gas, electrical power, fire and security. Richard has previously worked with Schlumberger, Shell Technology Ventures, Sensornet and Action. He's been responsible for introducing a range of new sensing technologies, and these include the first downhole fiber optic sensing system to the oil and gas industry. Richard leads the Bandweaver international team and is based in our Guildford office. So without further ado, over to you, Richard.
Well, thank you very much, Mark, for the kind introduction. Good morning, good afternoon, good evening, everyone. Thank you for taking the time to participate in our webinar. As Mark said, my name's Richard Kluth. I'm the Managing Director with Bandweaver Technology, and the subject of today's webinar is Going the Distance, Fire Safety Solutions for Long-Range Assets. And in this webinar, we'll look at the advanced capabilities of fiber optic heat detection with a focus on the performance at the longer range. So the objectives of the webinar, we'll start off introducing the principles of fiber optic technology and specifically fiber optic linear heat detection. We'll go on to demonstrate the benefits of the fiber optic sensors, and some of the points we'll repeat probably a number of times, but some of the key benefits are that you get coverage at all points along the assets, and that it's a robust and reliable technology leading to a low cost of ownership. We will show the enhanced performance of these systems, and that's rapid detection, even at the longer ranges, and extreme accuracy in locating fire events. And finally, we'll show Bandweaver's experience. We'll give examples of how the fire laser linear heat detection system is the highest performing system available, and give some examples of our case studies, which is a small subsection of the extensive experience we have in fiber optic linear heat detection. So the way we'll do that, start off with a history of fiber optics linear heat detection, give an overview of the fire laser linear heat detection system, go into what are some of the specific advantages of these systems, highlight this with some real life installation examples, and then finish up just giving you a short overview of Bandweaver, so a few key details about the company. So starting with the history of fiber optic linear heat detection, it goes back to the 1980s. The first examples of linear heat detection were road and rail tunnels, where it really capitalized on the longer range capability of these systems. As the technologies mature and improved over the years, we've seen a number of improvements. So resolution, that's both temperature and spatial resolution, increased range, although it was long even back in the 80s, this has continued to get longer. User interface, so the usability, the graphical user interface is much better, and speed of measurement is much better. Hand in hand, as well as the technology has matured, we've seen improvement in reliabilities. And as it's scaled up again and become more mature, we've seen a decrease in price. So we've really seen a widespread adoption of this technology, with more than 30,000 systems installed worldwide to date, and still growing. So when is this technology, fiber optic linear heat detection, when is it typically used? There's a number of factors that leads to this. So when the customer wants complete coverage, no gaps between sensing points, and as we'll continue to reiterate, it provides complete coverage. That's one of the key factors. Where you need a large number of sensors, this typically applies to large areas, large assets. Where it's difficult to test and maintain the sensors, either confined areas or difficult to reach areas, you can test this technology at any point, so it really overcomes some of the issues you have with sensing technologies that it's difficult to get into, and probably the most important, challenging environments. So where you have high humidity, dust or other particulates or explosive atmospheres that can really be challenging to legacy type technologies. The fiber optic is not affected by this, so it works brilliantly in these areas. Another element, we'll really tend to emphasize on is the early detection. This technology, because it measures fast, it measures at all locations, you can detect really early on. And with any sort of fire incident, the earlier you get it, where suppression can be, local suppression can be effective, you can start to bring the risk down and really control the fire and limit and minimize damage. If it's able to build up, you may have to get the fire department involved, and there's risk to infrastructure and personnel. So again, there'll be a focus on how do we stop the fire events as early as possible. So we've mentioned long range a few times. What do I mean by that when I say long range? Well, let's look at a few different technologies, and so we can compare. So if we look at smoke beam detectors, typical range for a beam detector is around about 100 meters. If we move to analog copper-based linear heat detection, you can go about typically 500 meters between the panels. With multi-point line type detectors, we have multiple sensors, electronic based. You can get up to 2.5 kilometers, but with the limitation that the sensing points are spaced quite far apart. You have a maximum of about 250 per line, so you're looking at sensing points that can be more than 10 meters apart. Digital linear heat detection, again copper-based cables. These can get up to 5 kilometers, which is entering into long-range territory. But with fiber optic, you can go up to 10 kilometers with a fire laser linear heat detection system. So that sort of leads to the next question. What kind of performance can you get at the longer ranges? So we'll look here at a number of the fire laser systems up to 10 kilometers, and then compare with other fiber optic competing DTS systems. So if we look at the 2 kilometer fire laser, as the name suggests, you measure 2 kilometers per optical channel. You get a measurement every 5 seconds. You get a measurement point every 1 meter. You can have up to 4 channels per unit, which means you can have a total coverage of 8 kilometers per unit, or 8,000 sensing points. If we move to the 5 kilometer, it's 5 kilometers per channel, 5 seconds and 1 meter again, 4 channels, up to 20,000 measurement points, 20 kilometers per unit. If we move to the 10 kilometer unit, again, 5 seconds, 1 meter, we keep it simple, same for everything, up to 4 channels again, so 40,000 measurement points per unit. That's a lot of sensors for one piece of equipment, gives you really good coverage. If we look at some of our competing systems, what we find of the competitors, it tends to do about 7 to 8 kilometers per channel, about 30 seconds per channel. Sometimes spatial resolution goes out to 4 meters, only a 1 or 2 channels at these ranges, meaning the number of measurement points, although a lot compared to legacy technology, it's much less than a fire laser unit. And this is based on the EM54 published specs that are readily available. So the next obvious question, how does the fire laser achieve such performance? I'll give a bit of overview to how we do this. So firstly, the systems are designed and optimized for fire detection. We're not using a DTS and then saying, well, let's use it for fire detection. We design from the ground up with fire detection in mind, with input from our customers. We're a very vertically integrated company, so the components are developed to our specification. We have a very rigorous quality system, which means we get fantastic, reliability. And we use 62.5 micron fiber, which means we get better performance. And I'll explain that more in the next slide. Later on in the presentation, I will go into more of the principles of optics technology, but I'll start just now talking a little bit about the fiber optic itself. So this is what carries the light, and the light is carried in this core, this central part. We use 62.5 micron, which means the part that carries the light is 62.5 microns wide. This is known as OM1 and is a telecom standard for multi-mode fiber. There's another standard called OM2, which is 50 micron, which is also used for DTS. We use it for many applications, but not in fire detection, but some of our competitors do. And I'll explain why we use the 62.5. The main reason is you get 53% more power in there. So the performance is 1.5 times better. So that's a real performance benefit by using the 62.5. It was established as the standard in the fire detection industry. So when we came in, it was already used a lot. We joined in that, we saw the extra performance, and also it gives more choice to the user. As of recently, only a single vendor used 5125 for fire detection. So if a user goes into that, they're locked into a single vendor. So there's more options available for the 62.5. 50 micron, it does have lower loss. So once you start getting longer than 10 kilometers, it's a very valid fiber. As we said, Bandweaver does use it, but not for linear heat detection. So we gave sort of characteristics of some of the applications for linear heat detection using fiber optic, and I'll just name some of the applications. So tunnels, road and rail, it's used a lot. Conveyor belts, whether it's mining for power stations, warehouses and hangars, manufacturing facilities, car parks, power stations, utilities, areas where there's ceiling voids, false ceilings, freezers, cold storage, you have high humidity, cold temperatures here, other high humidity environments, food industry, abattoirs, and increasingly solar panels. So this is a cross section. There are others, but these show a lot of the attributes that we talked about earlier. And when we give examples later, we'll pull from some of these. I'll give an overview of the technology now, starting with the principle of DTS, or distributed temperature sensing technology. So you'll hear it referred to this sometimes. Sometimes people just call it fiber optic linear heat detection. Some people call it distributed temperature sensor. But what distributed temperature sensor really means is the system uses standard grade telecoms fiber, and it uses something called optical time domain reflectometry, or OTDR, which is a bit of a mouthful, but as we'll see in the next slide, is basically very similar to time of flight for radar, but using light. But the key takeaway at this point is that the fiber is the sensor. You don't need any specific points, you don't need any engineering. The fiber does it itself. And I'll show you how. So the system, the way it's configured, you have the controller unit, a fire laser controller unit, and it plugs into a fiber optic cable that then goes into the asset. So the fire laser sends a pulse into this cable, the pulse travels down, and the reflected light travels back and is measured into the unit. The reflected light is proportional to the temperature, and by the time it takes the light to come back, the system can analyze and divide this into units of 1/2 meter. Typical for fire detection, we use 1 meter. That's plenty enough, and so it means you get a temperature measurement point every 1 meter. When you put this in your assets, you can then divide it up into this and effectively get coverage every 1 meter. So as I said, time of flight principle similar to radar. The fiber is the sensor, no dedicated sensors required, complete coverage, and simple installation and planning. You don't need to plan where you're going to put the sensors. You just lay the cable, and that's all you need to do. I'll just sort of reinforce this point by showing an example of how it works. So if we have a sort of a fire at this point in the assets, as you can see, you would measure the quickest at the hottest point above it. We have sensors everywhere, so you get it straight away above here. If the fire starts here, again, you have it above here. And if the fire's here, you get it wherever you are. You have you can measure directly above it. Means very fast, accurate detection. If we look at a line type point system where you have points spaced, perhaps every 10 meters apart, if the fire is here, it's between sensors, and so it would have a much slower response. The fire would have to build much more before the heat develops to here. Similarly, if it's here, again, a delayed response. Sometimes it will be directly below the point, but when you're doing system design and system commissioning, you have to take for the worst case scenarios. And so it's very important, the continuous coverage. I'll just give a introduction video here that'll give an introduction to the fire laser, and after that I'll talk over some of the key points. So there's a bit of repetition in the video here, but I'll talk through some of the features you saw in the video there. So we have the touchscreen LCD. You can have full functionality. You can have the temperature trace. This can be operated with a finger or stylus. We have the optical channel indicator showing which channel is active, other indicator lights, access panel for additional functionality, which is key lockable. As we saw, the operator did a alarm reset in the video. On the back, we have the fiber optic connectors. These are E2000 plug and play connectors. The integration either by RJ45 or serial ports for Modbus or for configuration of the system, 50 relays, and the power input 24 DC, which is often supplied through the fire control panel. The cable, the sensing cable, as we said, it's standard, based on standard telecoms grade fiber optics. So there's totally passive, no moving parts and no maintenance required. These things, they're not susceptible to corrosion. They can last, much longer than 30 years. Some cables have been in place for more than 50 years. It's a very robust cable. It's immune to electromagnetic interference, and you have no in-field power or network requirements, no comms. So it's very, very simple install. It's also very lightweight, flexible, about 3 to 5 millimeters typically. So very easy to install. We've got example of two of our fire fiber cables here, the AT or armored tube, which has a steel tube, wire and Kevlar, or the TT thermoplastic tube, which has thermoplastic tube and protecting Kevlar. This is a very typical sort of system architecture for fire detection. You've got the unit, which will be in a control room, a rack, or a wall-mounted unit. You then have the cable going out to the field. As we said, a single cable, that's the only element you need to install. The relays connecting to the fire control panel, and often communications to SCADA Modbus over TCP, to PLC, to building management system, ventilation control, SCADA. And some of our examples later will show examples of that. In addition to fire alarm information, you can also get absolute temperature data, which can be extremely useful. So some of the advantages of these systems, we'll divide it into three different categories. So the information benefits, you have precise temperature data. So again, you can use that, as I said, in many other systems. You have very low nuisance alarms. You can tune the zones, the environments to each specific environment. You get location accuracy, you're down to 1 meter, and very early detection with the smart alarms and the rapid measurement time. So getting all this information early allows the user to make much more improved decision making. You have the physical benefits, as we discussed, immune to electromagnetic interference, corrosion, intrinsically safe, no power or electronics in the field, unimpacted by movement, weather, environmental conditions. You have cut resilience and redundancy. So it's a very robust technology, which is often where it gets brought in when other systems have failed. And then you have the financial benefits. You have reduced infrastructure costs, minimum maintenance requirements, very long lifetime for the sensor cable, fast installation, you can be up and running in minimal time, so low total cost of ownership. And we'll run through that again later, talk that in more detail. So advantage we'll talk about in more detail now, redundant configurations, robustness against failure. We'll talk about the smart alarms and the smart zones, the advanced functionality you get around this, and the low levels of maintenance and high reliability you get, leading to low cost of ownership, low levels of false alarms. So redundancy options, with the fiber optic linear heat detection, you have different levels of redundancy. You have controller redundancy, which is typically you get in other technologies. If you double the number of or increase the number of units, you get redundancy. But we also have cable redundancy. So you have continuous operation in event of cable damage. This scales up, with a single facility, you typically need twice the number of units, but with the multi-channel capability, as you scale up to larger facilities, you get economies of scale. We've covered this in detail in previous webinars, so rather than me going into details here, I've got a link where you can go to our website. If you go to the resources page, you'll see there's an area for webinars, and you can see some of our previous webinars that goes into this in more detail. Also, if you message me, send me a mail at the end of this webinar, I'm very happy to respond as well. So smart alarms and smart zones. The advantages, as you get early detection, you can detect much faster than with conventional values. We've talked about the reduced false alarms. You can customize the triggers and the positions according to each specific zone, and again we'll go through some examples of that. And the fact you get the improved information, as we said, you integrate to other systems, ventilation, signal, and we'll give examples of that. So what are the smart alarms and smart alarms? So maximum temperature, this is similar to conventional sort of alarm setting, except you can configure it whatever level you want. The rate of rise, that gives you change in temperature, degrees C per minute, and deviation, and we'll talk through each of these smart alarms to give more detail. So maximum temperatures, with the fire laser, the alarm and pre-alarm can be defined at whatever level the user chooses. So you have an alarm and a pre-alarm level. As I said, you can set this wherever you want. what we find is with NFPSA and EN54, they have different categories. And so depending on how you configure in the system, you may do it differently for different categories. We see quite often in sort of standard type environments, 58 degrees C is roundabouts where the alarm temperature is set. But you do vary according conditions. And the important note is that it's defined in the software, not the hardware. So when we have conventional linear heat detection, copper-based systems, very often you have discrete levels depending on basically the material properties of the cable. So you have to pre-choose this cable in advance. Once the cable's in, you can't tweak it, you can't just change it in the software. You actually have to physically change the cable. And you've got very limited flexibility across different zones or environments. You'd have to actively change out the cable for the zone to change the level. So much less flexibility than with the fiber optic. The rate of rise, this allows you to trigger according to the change per minute. And one of the key benefits is it allows you to trigger much earlier. So if we imagine this is the temperature at a location in the event of a fire, so we're starting at a 20 degrees and the temperature is gradually coming up. What we would see here is 10 degrees per C minute is a typical range. So if this is time along here, it's going along, this is a minute, this is 10 degrees C. We're actually hitting the 10 degrees C at this point. And so you're triggering here at the 10 degrees C at 30 degrees C, and you're triggering it lower than a minute. So it's a fast trigger. If we were waiting for the maximum alarm set at 58 degrees C, which I mentioned is the normal, you'd be waiting more than 2 minutes. And this is a good backstop to have in. There's still a place for this, but typically rate of rise is one of the smart alarms that triggers earlier. The other alarm we mentioned was deviation, and deviation can be very effective when you have a slow fire. So if we take the example here, we've got a rail track, we have a small fire developing here. What we'll do is we'll look in this top graph here at how against time, how the temperature develops at this point. And then this point will be the graph along the whole distance, and we'll see how this small fire develops. And what we'll see is you can see the fire starting to grow. You can see the temperature starting to increase. This is a minute, this is 10 degrees C. What we see after a minute, it hasn't triggered. But at the bottom here, we can see this event going, and there, it's gone above the 10 degrees C. It took more than a minute, but the deviation alarm will trigger. So basically, it's used often where you have slow developing fires. We see this very commonly used in car parks in countries where small fire pan tests are obligatory for commissioning, and sometimes it's too slow for the rate of rise. So we'll give an example of that in our case studies. And finally, on the smart alarm, smart zones, the zones themselves, you set these in the software and it gives you complete flexibility in design and definition of the zones. So this is an example of the user interface when you're defining them through the software. You can have up to 1,000 zones. You can have complete flexibility. The zones can be overlapping. You can have different outputs. When you're coming in, you name the zones, you say whether they're active, which optical channel, which relay do you want to configure, where does it start, where does it stop, and then the different levels, maximum alerts, pre-alerts, change rate deviation, even minimum if you want, if you're going cold. That's more for leak detection than fire. And so very simple interface for programming. So we talked about, the whole life costings. What we'll do here is we'll work through this. We'll go around, look at design, procurement, installation, operation, maintenance, downtime, capital costs, and then we'll look at some of the softer, more reputational costs, such as image, sustainability, and health and safety. So starting with design, you have much lower costs. No need to position each sensor, a single cable. It's a very simple system design. You just really need to think about the spacing. This then leads to lower procurement costs. You've only got the controller and the cable, the fixtures as well for attaching the cable, but nothing else in terms of what else goes out in the field and in the control room. Installation costs, you've got a single cable, no infield power or communications, so very low installation costs, both from a material and a labour point of view. Ongoing operational costs, a simple annual test, which can be done anywhere on the cable, so very simple. You know, almost no maintenance for the cable, very low, you know, no upgrade costs. You can do firmware upgrades, but it's very, very low. A very robust architecture, so you have no downtime costs. So it's a very, very cost effective from that perspective. And the capital cost also can be very low if you have large areas, you know, good economies of scale, large number of sensing points. So it's very favorable compared to other technologies. Moving on to the sort of reputational costs, you know, public image using a high technology. A lot of companies like this, it feeds well into their image. Sustainability, it's environmentally friendly. There's no batteries in field, low power. You don't have any the environmental issues and batteries, none of the maintenance issues. And from a health and safety perspective, it's intrinsically safe. You don't have any, you use a safer ATEX, explosion-proof environments, very fast response time. So what we find is, you know, customers, when they go through these whole life costings, they find it very effective, and often, you know, will choose this technology over legacy technology types. What we'll do now is we'll look through some real life installations that Bandweaver or our partners have installed. Tunnel protection using linear heat detection. We'll look at the Santa Lucia tunnel in Italy, which is the largest 3-lane tunnel in Europe, and the KMO in Turkey, which is the longest 4-lane tunnel in the world. Conveyor belt, the Yenikov power station in Turkey, which is feeding a power utility with coal on it. A car park in the Netherlands, which has more than 7 kilometers of cable in a single car park. And we'll look at Istanbul Airport. We're looking at hangar protection where there's more than 8 kilometers in a single hangar. And we'll also just briefly touch on Istanbul Airport, that there's a number of fiber optic fire laser systems across the airport. But starting with the Santa Lucia tunnel, this was won and installed by our partners RAET in Italy. As we said, it's the longest 3-lane tunnel in Europe. This is a very high profile project. It was an extended tender process. This was the key component of the safety system, so very heavily scrutinized. And so it was a very prestigious project to win. You can see a picture of the tunnel there. And I like this picture here. It shows the scale of how big the cutters were, and you know how big an operation this was to build this tunnel. So the system configuration, the tunnel's 8 kilometers long, 13.7 meters wide. The sensors were positioned at 7.2 meters at 2 locations across the tunnel. And we had a full system and cable cut redundancy. So when any system is taken out of service or any damage to any of the cables, you still have full functionality. You would receive an alarm, they will receive an alarm, but they continue to operate. We have a picture here of one of our R&T employees and Autostrada in the power distribution room. You can see the unit here in the control room. I just want to emphasize the touchscreen LCD. We saw it in the video. The feedback we had from Autostrada in this is that it was, you know, used very heavily, very simple, very effective interface that they really use a lot on an operational day-to-day basis. Integration with the SCADA system. We have a screenshot of the SCADA software here. We have a close-up here where you can see the actual temperature is being built in, you know, on a zonal basis. So you see the maximum temperature of each zone in there. And there's a lot of zones for this project, 982. They have it every 10 meters. That was dictated by the extinguishing system. So it's connected to multiple systems, the extinguishing, ventilation and lighting, but the extinguishing required every 10 meters. And the fire detection systems are also linked to, you know, the smoke detection and CCTV, but only the fire laser was used for alarming because of this, that it could divide it into 10 meters and then link back to the extinguisher. So it really is, you know, absolutely critical system for autostrade in this tunnel. Just touching briefly on another tunnel, the North Marmara Highway KMO tunnel, which was installed by BTS Yangin, our partners in Turkey. We can see a picture of the tunnel here, so wide that you can fly a plane through it. We'll have a quick look at that later. It's the longest 4-lane tunnel in the world. Along the highway, we did 8 tunnels in total. So BTS installed 76 kilometers of fiber for fire laser in these tunnels. Again, redundant loop configuration, so that if there's any cut to any of the cables, you have complete cable redundancy. Again, connected to the SCADA system. You can see the control room here, the SCADA system, and connected to the fire control panels via the relays. What we'll look at now is we'll look at the a video of the commissioning process. We'll see them lighting the fire pan, and we'll see the SCADA system alarming. You'll see a timer in the top left-hand corner of the video, which shows, you know, how long the system took to alarm. In this case, just over 30 seconds. So that gives you an idea of the commissioning test and how quick the system can respond. I showed a picture of the plane flying through the tunnel they used as a promotion for the video for Red Bull. I'll just show a quick video of that because it's quite a feat. Pretty amazing stuff. Okay, moving on to the Yennikov power station. This is monitoring of a coal conveyor belt. The Yennikov power station is a very large power station, 420 megawatts. It's owned by Limac. It moves 10 millions of coal per year through the conveyor belt system. And they've had a number of issues over the years with the bearings in the rollers seizing up, heating up, and causing fires. It's really critical power infrastructure, highly flammable product, which requires advanced detection. And so they're really looking for something that can detect fires early and prevent any disruption and damage to the conveyor belt. In this case, there's more than 20 kilometers of conveyor belts monitored, and because there's a lot of different sections, they really wanted advanced visualization. So we'll show with the MaxView software how that was carried out. So there's a single 10-kilometer 4-channel fire laser. It's up to 40 kilometers of monitoring, 714 zones, 30 meters each zone, the total of 21.5 kilometers, so 21,500 active measurement points. And they configured the alarms so the maximum temperature was 57 to 61.5, rate of rise 5 to 7 degrees C per minute. The system was integrated both with the Panasonic CCTV using relays and also using MaxView. We'll show some installation pictures. This was carried out. The contract whole thing was managed by BTS Yangin, again, our partners in Turkey. So you can see the interface in the control room here, the fire laser in the instrument rack, installation of the cable in the field on the conveyor belt, and a customer training session. So as I mentioned, they wanted advanced visualization, and this is an example of our MaxView software. So we can see here, this is the entire length of the cable. Each of these tags is a label of one of the sections. If you click on this, it brings you through to the details of this section. Equally, you can click on the route menu. So if you click on the route menu, you get the view here, in this case, the section OPA 6566. And so you can see the path of the fiber here on the conveyor belt. You have it on a map photo view here. There's 20 zones per side here. And so when there's any alarm, it will show you precisely which zone is triggering and where it is on the conveyor belt. In other sections, for example, 3031 DOCUS, they choose to use a schematic. There's machinery here. It was felt it was more useful to show the schematic than a map. And MaxView has that flexibility to change according to the customer's requirements. In this case, very, within the first 12 months of installing the system, a hot roller was detecting using the rate of rise of alarm, and a fire was prevented. So it's already proven to be very useful. When the hot roller was detected, it was isolated to within 30 meters. The maintenance team go to the zone upon alarm, use a thermal camera to corroborate, and then take the action. In this case, the roller was glowing hot at the time. It was very easy to spot even without the camera. And the roller was replaced, and further damage and fire was prevented in this case. So fantastic case study. Moving on to a car park in the Netherlands. This is an indoor car park, a dusty environment. Exhaust fumes can be very challenging for smoke detectors. This car park had almost 7 kilometers, 7,000 sensing points, and again installed in a loop configuration with an 8-meter spacing between the cables. We can see pictures of the cable installed at ceiling level here. You can see how it can adapt to changes in ceiling height. Very flexible cable, and see it in different configurations. In the Netherlands, all systems must pass the fire pan commissioning test. This is a pretty small pan, 1/2 meter by 1/2 meter, with either 1.2 or 2.4 litres of ethyl alcohol, depending on the wind speed. Ceiling height typically 2.5 to 3.5 meters. Normally, the rate of rise deviation are either 7 to 13 degrees C per minute or 10 to 15 degrees deviation. We'll look at a video of a test here. In this example, it sounds within 20 to 5 seconds. There was a high, we'll see the wind speeds high, so it's a 2.4 litre test. You can see the fire pan here, you can see the cable here. It's installed at this point here. In the video here, we'll see our colleague at SenseTech, who installed that, was lighting the fire pan test, walking away to area of safety. The cable is here at this point here. He's now joining the colleagues from the fire department, the Netherlands Fire Department. You can see the wind speed 1.6 meters per second, and you can hear the alarm going at that point after 25 seconds. Interesting that this started at 5 degrees C background temperature. The alarm actually alarmed at 12 degrees C, the maximum temperature of this fire pan test, because we can obviously measure all around it. It was only 25 degrees C. There wasn't too much spreading along the length of the cable, so you wouldn't be able to pass these fire pan tests with conventional linear heat detection. And this is becoming the de facto standard in the Netherlands for car park monitoring. As we said, tests are mandatory, copper-based, not sensitive to pass this. Finally, Istanbul Airport. So one of the largest international airports, 200 million passengers per year, 6 terminal buildings, biggest IT project in Turkish history. The subsystems must seamlessly integrate. There's building management systems, fire control panels. The fire laser with the Modbus and the relay is able to integrate to multiple systems. The airplane hangar had 3 fire laser systems deployed. This is a very large maintenance hangar, 65,000 square meters, multiple fire detection technologies. The fire fiber was 8,000 meters of it installed at the cable level, cable tray level. And we can see here the length that's run backwards and forwards in 4 separate zones, installed using steel wire. Also in the airport, the fire lasers installed in a number of different road tunnels, 2 separate hangars, different cable galleries, for a total of 18 fire laser systems at the time of writing. It's still going up. So you know, fantastic use of technology throughout the airport. Okay, well, I'm just going to finish with some facts on Bandweaver, a bit of background to us. So we've been around 20 years. We formed in 2002, so our year of 20-year anniversary. We've installed more than 7,500 systems, installed more than 60,000 kilometers of fiber optics around the world. We have more than 300 people across the group. And the key technologies we focus on are distributed fiber optic technologies, namely temperature and acoustic sensing. We have a global presence across the world. I'm based out of our UK office, as we mentioned. We work to a number of international standards applicable to various industries. You see some of the standards here. We also spend a lot of time focusing on reliability, and our mean time between failure is greater than 29 years and increasing all the time. We have an international customer base. Here are some of the customers we work with. You know, we have a number of repeat customers. We're a trusted supplier, and we're continuing to expand this customer base. I'm very keen to do so. So in conclusion, the key points we talked about. So fiber optic linear heat detection provides complete coverage at all points along whatever asset you install it is in. It's a robust and reliable technology with a very low cost of ownership. Has enhanced performance versus conventional systems with the rapid detection, the smart alarms, the improved information. We have the highest performance system available with the fire laser. And Bandweaver with extensive experience in fiber optic linear heat detection applications, so we can help you with whatever your requirement is. So thank you very much for listening to our webinar. Really appreciate the time, and I'll pass back over to Mark for some of the questions I look forward to answering.
Thank you, Richard. Very informative and educational presentation. As usual, when we do these webinars, we've got many questions, which we unfortunately are not going to get through today. For people, as per my introduction, if we don't answer your question today, please drop Richard a direct email. His email address is up on the screen now, but we'll try and get through as many we can in the next 10 minutes or so. Okay, so the first one. So you mentioned your system can detect, but can it detect multiple fires simultaneously?
Yeah, no, it's a very good question. Something we get asked a lot. Yes, the answer is there's no limit. It's you know, it's digital information that's coming through the fiber optic sensors. So in theory, it could take one at every point along that. There's really no restrictions. As we said, your zones, you can configure up to 1,000 zones, which is plenty enough for most people. But yes, it can detect multiple events. Yeah.
Okay, thank you. There's a question around MaxView. Can our MaxView display color-coded temperature representations in an area where you can see visually the changes of temperature? Yes, can do. You can have the color coding on the display along the cable. You can have the alarms on there. You know, again, it's very flexible how to do that. You can have also have the complete temperature trace on there. You know, different customers have very different requirements with that, depending on their specifics. But yes, that is something that gets asked for. Okay, thank you. And then there's a question about our cable. What is the maximum temperature that the fiber optic cable can stand up to in case of fire?
So there is this is an excellent question. We get this asked quite a lot. We do carry out tests to 750 degrees C for some cables. There are some customers that want it to survive for a certain amount of time at those levels. So the glass itself melts at 1200 degrees C, I believe it is. So again, very robust. But as standard, we rate the cables to 85 degrees C for standard fiber optic. So it can survive for shorter temperatures a longer time. But if you go above 85 degrees C as standard, we would recommend that the section of cable that has experienced that is inspected or replaced. If you want to go higher than that, it is possible. There are specialist cables that can go higher than that, but for the multiple of applications, the rating is 85 degrees C, but with the ability to collect data for extended period at temperatures up to 750 degrees C, if that makes sense.
Yep, that's great, thank you. So a question about redundancy, and you talked about cable cut redundancy. In the event that the cable is damaged, can it be repaired? Does it have to be recabled? And then does the system have to be reconfigured to continue working?
Okay, they're very, very good questions. Yes, the cable can be repaired. It needs a telecoms, whoever installed it, or a local telecoms engineer can do that in a fairly straightforward manner, because it uses telecoms cables. So you just splice in the section of cable. Typically, yes, you need to reconfigure the system, a minor modification if you're changing the length of the cable. So there's two ways of doing it. Some customers use a maintenance loop, where you would take the slack from the maintenance loop to splice it in there, so you're not actually putting any additional cable in which case you likely wouldn't need to reconfigure. Or you might use an additional section of cable to splice in. You might have an extra 5 meters, and so you just need to add an extra 5 meters to the length. But it's a very simple configuration. Okay,
thank you. Question around the lasers that are used within the DTS. Are the lasers dangerous? And if the cable is cut, could it cause any damage?
Yeah, no, very important, very good question. No, all of our systems are class 1M lasers, and a label on the back as such. And what class 1M means is that it's even if you shine it in your light, it can't damage. You need to actively focus it with a focusing device to cause any damage. But then also the wavelengths are outside the retinal hazard zone, which means it can't do any damage to the eyes. To all intents and purposes, no, it's not possible. They're very, very safe. Equally, in explosive atmospheres, the power is so low that it cannot cause ignition, and so it cannot, very safe from that perspective. So can't do damage to people and can't cause any form of ignition or any kind of heat. It's not like a welding laser or anything. It's much lower power than that. Yeah.
That's very good to know. Okay, so next question. Does your system have a lead-in cable, or is the system sensitive and measuring from the back of the unit?
Yeah.
And yeah, so that's it. Sorry.
Yeah. Sorry. Yeah. Yes, it does. It does measure from the back of the unit, so the whole of the cable is sensitive. But some people choose to use it as a lead-in thing, so it's measuring and sensitive, but you don't have to set up the alarms in that, so the system can completely ignore it. So we find that you may have hundreds of meters sometimes between the controller and where you actually want to start measuring. So in the software, you start the zones at the relevant area, but yes, it is measuring at those points. But for some people, that may not be an area of relevance.
Great, thank you. Time for a few more. Okay, next one. Your webinar covers linear heat detection, but can you use your DTS in other applications, e.g. For are your products suitable for monitoring cable trays?
Yes, and actually cable trays is a very interesting one, because for one of our key areas for monitoring is power cables, and we usually do it from a capacity management. So we've also got a team of power cable experts that are able to thoroughly model cables. So a completely different area and very different level of expertise. The systems there can go up to greater than 50 kilometers. So it's a longer range, different level of expertise. But sometimes with power cables or cable galleries, sometimes we get asked to monitor for the capacity range, and sometimes for fire detection. So sometimes you may even have two systems measuring the same tunnel. But yes, we do. We also do pipelines, leak detection, environmental monitoring, borehole, dam monitoring. Yeah, there's a lot of areas, and we have other different systems that are focused on that, for optimized for that.
Okay, thank you. Just time for one or two more. Can you clearly explain how you integrate your DTS controller into a fire panel?
Yes, yeah. So the main method of integrating into the fire panel is using the electrical relays at the back. So they will connect. There's 50 of them, so you can have 50 defined zones coming out of the backs. 6 of those are system, and so 40 for our user defined. And it's a very sort of simple standard method of connecting to the fire control panel. We often find customers as well will take the Modbus output that we said that goes to the SCADA or the building management system, but often that's a different aspect, and it's the relays that that connect to the fire control panel.
Great, thank you. Next question. What is the most number of systems installed in any specific project or network? So what's the highest number of controllers on any one project?
Yes, gosh. So let me think. So well, we showed the example of Istanbul airport. That was 18 and counting, so that was going up. But I think the largest are some of the large scale metro installations. I believe one of there's a city in Asia where 78 across the entire metro network. So that's a lot, and we've got quite a few installations sort of between 20 and sort of 70. And what we often see is that the user often installs them in phases, so it's unusual to put them all in one go, but they'd sort of build one line at a time, and it might be 10 per installation. I can think of other warehouses. There's some warehouses where there's 10 or 11 per warehouse and multiple warehouses. But yeah, I think about 75 is the most for a single project.
Thank you, Richard. Unfortunately, we're now out of time, so I'd like to thank everyone for joining today, and obviously thank you for Richard for providing excellent presentation on Bandweaver's linear heat detection. Richard's details are up on the screen, so you can fire any questions we haven't got round to today across to him by email, and we'll be sending out the webinar, a recording of the webinar, to everyone who's joined, so you can watch it again in your own time. Over to you, Richard, just for closing.
Okay, well, thank you very much, Mark, and Thank you again, everyone. Yeah, hopefully you've had a chance to take down my details, but as Mark said, we'll send out details and you can pick it up for the website. So thank you very much and have a great day, a great evening. Thank you.